Hello everyone, and welcome to Stuff I Found Interesting. Today's rabbit hole is supermassive black holes. The same supermassive black holes that are incredibly massive objects that exist at the centers of most galaxies, including our very own Milky Way. They are characterized by their enormous mass, which can range from millions to billions of times the mass of the Sun. There are a few different models that astrophysicists have used to explain the formation of supermassive black holes. The first model says that supermassive black holes are thought to form through the collapse of massive clouds of gas and dust in the early universe. As matter falls into the black hole, it becomes compressed and heated to extremely high temperatures, emitting vast amounts of radiation and energy. Despite their name, black holes do not actually suck matter into them. Rather, they exert a gravitational pull that becomes stronger the closer the object gets to the black hole's event horizon, which is the point of no return beyond which nothing, not even light, can escape. Any matter that crosses the event horizon will inevitably be drawn into the black hole and crushed into an infinitesimal point at the center, known as the singularity. This is called the direct collapse model. Another proposed model, called the merger-driven growth model, involves the growth of intermediate mass black holes through the merger of smaller black holes and/or the accretion of gas and dust. Over time, these intermediate black holes could merge with each other to form larger black holes, ultimately resulting in the formation of a supermassive black hole. The next potential model of the creation of supermassive black holes is called the runaway stellar collisions model. In some scenarios, supermassive black holes could form from the collapse of large clusters of stars that have undergone a runaway process of stellar collisions. These collisions would produce massive stars that would then collapse into black holes and then merge with each other to form a supermassive black hole. Supermassive black holes are believed to play a key role in regulating the growth and evolution of galaxies. As matter falls into the black hole, it releases enormous amounts of energy that can drive outflows of gas and dust, thereby regulating the rate of star formation in the galaxy. Supermassive black holes may also be responsible for the powerful jets of particles and radiation that are often seen emanating from the centers of galaxies. Despite their importance, many aspects of supermassive black holes remain poorly understood, and they continue to be a subject of active research and study in astrophysics. Since they are by no means completely understood, we have many open questions regarding supermassive black holes. While it is generally understood that supermassive black holes form through the collapse of massive clouds of gas and dust, the exact mechanisms by which this occurs is not well understood. For example, it is not clear how gas is able to accumulate into the central regions of galaxies in sufficient quantities to form supermassive black holes. We also don't know how supermassive black holes evolve over time. While it is thought that they grow through gathering more matter trapped in their gravity wells, the details of this process and the factors that govern it are not well understood. Additionally, it is not clear what happens to supermassive black holes over extremely long timescales, like trillions of years, or whether they eventually evaporate through processes such as Hawking radiation. The physics of how matter accretes into supermassive black holes is complex and poorly understood. In particular, it is not clear how the accretion disk around the black hole is able to generate the intense radiation and jets of particles that are often observed. These jets are known as relativistic jets and can extend for thousands of light years from the black hole, emitting radiation across the electromagnetic spectrum. The exact mechanism by which supermassive black holes produce these jets is still a matter of ongoing research, but there are several proposed models. As matter falls into the accretion disk around the black hole, it releases large amounts of energy in the form of radiation and heats up the surrounding gas and dust. This can drive powerful outflows of particles and radiation that form the jets. Another proposed mechanism involves the interaction between the accretion disk and the magnetic fields that are thought to be present in the vicinity of the black hole. As matter falls into the disk, it becomes ionized and can interact with these magnetic fields, leading to the acceleration of charged particles and the formation of the jets. The rotation of the black hole itself may also play a role in the formation of jets. As matter falls into the accretion disk, it can be dragged along by the rotation of the black hole, creating a twisting helical structure in the jet. Regardless of the exact mechanism, it is clear that supermassive black holes are capable of producing extremely powerful jets of particles and radiation that can have a significant impact on the surrounding galaxy. These jets can affect the temperature and density of the interstellar medium, drive large-scale outflows of gas and dust, and regulate the rate of star formation in the galaxy. We also don't know anything about the interior of a black hole, including the singularity at its center, as it is hidden from observation and is not well understood. It is not clear what happens to matter once it crosses the event horizon, or how it interacts with the singularity. It is possible that all matter that crosses the event horizon just adds to the mass of the singularity. We have no way of knowing with our current tools. We are also unsure of the relationship between the supermassive black hole at the center of a galaxy and how that galaxy evolves. While it is believed that supermassive black holes play a key role in regulating the growth and evolution of galaxies, the details of this relationship are not well understood. For example, it is not yet clear on how the properties of the black hole, like its mass and spin, are related to the properties of the galaxy, like its size and structure. One school of thought behind this relationship is that the supermassive black holes can regulate the rate of star formation in their host galaxies through a process known as feedback. The basic idea is that as matter falls into the accretion disk around the black hole, it releases a large amount of energy in the form of radiation and jets of particles. This energy can then interact with the surrounding gas and dust in the galaxy, heating it up and preventing it from collapsing to form new stars. The exact mechanism of this process is complex and not well understood, but there are several ways in which feedback from a supermassive black hole can affect star formation. The radiation and jets emitted by the black hole can heat up the gas and dust in the galaxy, preventing it from cooling and collapsing to form new stars. The energy released by the black hole can also drive large-scale outflows of gas and dust from the galaxy, which can remove material that would otherwise be available for star formation. The energy released by the black hole can create shocks and turbulence in the interstellar medium, which can prevent gas from collapsing and forming stars. The net effect of these processes is to reduce the rate of star formation in the galaxy. In some cases, feedback from a supermassive black hole can even completely shut down star formation, leading to the formation of a dead galaxy. Of course, none of these mechanisms are fact, and the world's astrophysicists are still gathering data and debating over what they think supermassive black holes are capable of. From all the galaxies that we have observed so far, it is believed that most, if not all, galaxies contain supermassive black holes at their centers. Observations have shown that supermassive black holes are common in massive galaxies and are typically located at the center of those galaxies. One line of evidence for the existence of supermassive black holes in galaxies comes from the observation of high-velocity stars and gas clouds orbiting around a central point. These orbits can only be explained by the presence of a massive object with a strong gravitational field, such as a supermassive black hole. In addition, observations of quasars, extremely luminous objects powered by accretion onto supermassive black holes, have shown that these objects are common in the early universe, suggesting that supermassive black holes were already present in the first galaxies. However, not all galaxies are equally likely to host supermassive black holes. Small, low-mass galaxies may not have enough gas and dust to form a supermassive black hole, while galaxies that have undergone major mergers may have disrupted their central black holes. Nonetheless, supermassive black holes are believed to be a common feature in most galaxies, including our own Milky Way. I tried finding out if there was anything inherently different between a regular black hole and a supermassive one, besides the obvious size difference. If you leave a regular black hole alone and keep feeding it mass from the surrounding area, would they all eventually evolve into what we would recognize as a supermassive black hole, and then go on to become the center of a new galaxy? At present, there is no definitive answer to whether singularities at the centers of supermassive black holes are different from those in normal black holes, as details of these objects remain poorly understood due to the extreme conditions at their centers. However, some researchers have proposed that there may be significant differences between the two types of singularities. One idea is that the singularities at the center of supermassive black holes may be fuzzier or stretched out compared to those in normal black holes, due to the effects of quantum mechanics. According to some models, as the mass of a black hole increases, its singularity may become less defined, with the quantum fluctuations of space-time becoming more significant. This could lead to a fuzzball or fuzzy sphere model of the singularity, in which the singularity is replaced by a diffuse quantum mechanical structure. Another proposed difference is that the singularities in supermassive black holes may be surrounded by a firewall or a layer of intense radiation and energy that would prevent anything from passing through the event horizon without being incinerated. This idea is highly controversial, and there is no consensus on whether such a firewall would exist. We have too little data to come to anything resembling a definitive call on any black hole. The best we can do at the moment is to keep imaging the universe around us with telescopes like the James Webb Space Telescope, so that we can start making more educated guesses about the natures of black holes or any other mysteries of the universe. Just for fun, I tried to find out what would happen if two galaxies collided and their central black holes combined. I remember reading somewhere that the Andromeda galaxy was on course to hit our Milky Way galaxy in a few billion years. After looking this up, I found out that the Andromeda galaxy has already collided and merged with another galaxy long ago, and the Milky Way will follow in about 5 billion years. And even more crazy news than that, the Milky Way is currently colliding with and absorbing a few smaller dwarf galaxies right now. Anyway, sorry for the tangent. If two galaxies collide and their central black holes merge, it can result in a spectacular event known as a black hole merger or black hole coalescence. This process can take millions of years to unfold and is thought to be accompanied by the emission of intense gravitational waves. As two black holes approach each other, they begin to orbit around each other, gradually spiraling closer and closer together due to the emission of gravitational waves. The strength of these waves increases as the black holes get closer, causing them to lose energy and spiral in faster. Finally, the black holes merge into a single, more massive black hole, releasing a burst of gravitational waves that can be detected by observatories on Earth. The process of a black hole merger is thought to be a key driver of galaxy evolution, as it can release enormous amounts of energy and disrupt the structure of the host galaxies. In particular, the merger of two massive galaxies can trigger a burst of star formation and the formation of new, more massive stars. However, it is important to note that black hole mergers are relatively rare events, and the vast majority of galaxies are not currently undergoing such a merger. Thank you all for taking the time to learn with me. No matter who you are, you only get 24 hours in a day. Thank you for spending a portion of it with me. If you liked what you heard, please consider subscribing. If you did not like what you heard, thank you for sticking with me this far. As always, if I missed anything or get anything wrong, please let me know, as I would love to learn more. See you next time.